So, I want you to imagine something. Imagine you invent a tool that millions of people use, something that literally defines an entire industry. And then, at the absolute peak of your career, you get up on the biggest stage there is and you tell everyone that the whole thing is built on a fundamental flaw? Well, that's exactly what computer scientist John Backus did back in 1977. This is the incredible story of his Turing Award lecture, a speech that basically questioned the very soul of programming. See, to really get why this was such a big deal, you have to understand who John Backus was. By 1977, the guy was a living legend. He was the head of the IBM team that created Fortran back in the 50s, a language that had already changed the world. As the person giving him the award said, pretty much everyone in that room knew his work inside and out. He wasn't some outsider with a crazy idea, he was the ultimate insider.
So when he stepped up to receive the Turing Award, which is basically the Nobel Prize of computer science, everyone was expecting a victory lap, right? A nice speech about the good old days of Fortran. But instead, he dropped an absolute bombshell with a title that was also a question. Can programming be liberated from the von Neumann style? He wasn't there to pat himself on the back. He was there to challenge the entire future of his field.
So let's really set the stage for this pivotal moment. This was not just some random conference talk. This was the equivalent of winning an Oscar for Best Director and using your acceptance speech to say that movies are being made all wrong. Backus had the biggest microphone in his world, and he used it to question the very foundations he himself had helped build. What a move. Okay, let's get to the absolute heart of his argument, which he gave this brilliantly simple name. Backus said, look, all of our programming languages, his own Fortran, others like Algol, you name it, they all share a common ancestor. They were all designed to work on one specific kind of machine, the von Neumann computer. And this basic design was already 30 years old at the time. He boiled this architecture down to its absolute essence. You've got a brain, right? That's the CPU. You've got a big warehouse full of data, which is the memory, or what he called the store. And this is the critical part. You have a single, skinny little tube connecting the two. And this is where he lands the punch. Every single piece of data, every instruction has to get pumped one little word at a time back and forth through this tiny tube. This, he declared, was the von Neumann bottleneck. What a perfect name for it. But here's the real kicker. He said this wasn't just a hardware problem. This physical limitation created an intellectual one. It forced programmers to think about problems not in big, sweeping ideas, but in this tedious, step-by-step, word-at-a-time way, just to manage all the traffic going through that tiny bottleneck. And this bottleneck, he said, had split the world of programming right in two. And Backus, well, he did not pull any punches. He called the languages that grew out of this model, the ones everyone was using, fat and flabby. He said they were getting bigger and more complicated, but not fundamentally better, because they were all trapped in this word-at-a-time way of thinking. He painted this picture of a kingdom divided. On one side, you have the world of statements, loops and assignments, which he saw as this chaotic mess, all about changing data and memory one little piece at a time. And on the other side, you have the clean, orderly world of expressions, like mathematical formulas, which have these beautiful, predictable properties. The problem? The messy, chaotic world was running the show. So to make his point completely undeniable, Backus decided to show everyone, not just tell them. He put the two styles head-to-head in a classic showdown. He picked a pretty common operation called the inner product. Now, you absolutely do not need to be a math whiz to get this. Trust me. The entire point is in the visual contrast between the two ways of writing a program to do the exact same thing. Just look at this. On the left, you've got the traditional von Neumann style. You can see that word-at-a-time thinking in action. Set up a counter, start a loop, grab one thing from A, one thing from B, multiply them, add them to the total, increase the counter, and do it all over again. Now look at the right. That's his proposed functional style. It's dense, sure, but it's one single static definition. No loops, no counters, no step-by-step chore list. Let's just break down what's so clumsy about that program on the left. To even understand it, you have to run it in your head, step by step. It's all about individual words of data. And all the boring housekeeping stuff, the loops and counters, it's all mixed in with the real work. Plus, it's not very general. It's hardwired to work with those specific variables. Now, compare that to the functional program. It's a whole different universe. You understand it just by looking at its structure, not by running it in your head. It works with big ideas, whole conceptual units like transpose this, or apply this to everything. All the housekeeping is hidden inside these powerful, reusable operators. And it's totally general. It defines the idea of an inner product that you can use on anything. So, what was his grand solution to all this? Well, it was brilliant. He wanted to make programming more like something we all learned back in school. This was the revolutionary idea at the core of it all. Backus basically asked, what if we could manipulate our programs with the same kind of certainty and formal rules that we use in algebra? And this slide just illustrates that parallel perfectly. On the left, he's got a rule from algebra we all know, the distributive law. On the right, a law from his algebra of programs. It looks complicated, but all it's saying is that doing two things to the result of a third thing is the same as doing them each separately. The point is, programs become things you can actually transform, simplify, and even prove correct. And why does that matter? It's a total game changer, because it makes reasoning about your code a natural part of programming. You don't need some other complicated system of logic to talk about your programs. You can reason with the programs themselves, using the laws of this new programming algebra. So, the big question is, did he succeed? Did John Backus's call to arms actually liberate the world of programming? Well, the revolution wasn't exactly an overnight success. We still live in a world that is dominated by that von Neumann architecture. But the ideas from that 1977 speech, they planted a seed. Concepts from functional programming, like operating on a whole list of things at once instead of one by one, have slowly but surely found their way into almost every single mainstream language we use today. So, did Backus achieve his goal? The von Neumann bottleneck is definitely still with us. But maybe, just maybe, liberating programming was never about winning one single battle. Maybe it was about giving programmers a new way to think, a whole new set of tools, and a new language to imagine a future beyond that word-at-a-time world. And if you look at it that way, John Backus's radical idea is more alive today than it has ever been.